In this final lecture, we're going to calculate our formwork strength to ensure that it is adequate to resist the pressure from the concrete. So here we have an out-of-plane shear stress from the resultant of the pressure, and we have an out-of-plane flexural stress from the hydrostatic pressure. First, we can calculate the resultant using the pressure triangle on the long wall, or the worst case scenario that I've circled here in blue. Remember, we have a 40 centimeter by 70 centimeter internal structural concrete column that's being cast. So we have along this 70 centimeter wall, we have hydrostatic pressure from the concrete, and this wall is going to be supported on either side by its connection to the other walls. And I've drawn what the pressure distribution would look like on the formwork if we were just looking at that one wall, and then drawn out more of an isometric view with the length of the wall being that 70 centimeters and the height being the height that we actually pour or place the concrete to. We have our pressure resultant that's going to be at 1/3 of the height from the bottom, and we'll assume that this is acting at the center of the wall because it is symmetrical here. That gives us a shear value of R, our resultant, over 2, and a maximum moment value of RL over 8. If we model the wall here as a fixed beam. So the resultant, I got ahead of myself for a moment, the resultant is going to be equal to our maximum pressure that we take from the equation in the previous lecture, times that L, or times that width of 70 centimeters, times height of the placement of the concrete, and divided by 2, because remember this is a pressure triangle, so it's pH over 2 to get the area of that triangle, which is the resultant. Like I said, we can model the form as a fixed beam with a point load at the center to get our maximum shear and moment of R over 2 and RL over 8. And I've drawn these out for you, or summarize these for you, as well as where our shear stress is going to be 3R over 2A for a rectangular section, and our maximum flexural stress is going to be our maximum moment divided by the section modulus. So we can take the shear stress of the area that is actually resisting shear that I've shown in this dotted black line here. It's going to be our length, or 70 centimeters, times our width, which is going to be the 15 centimeter width of the brick formwork. So that's going to be our area, L times W, in our 3R over 2A equation. Now for flexural stress, our section modulus is going to be, once again, our length times our width squared over 6 for a rectangular section. So that gives us, when we plug it into the equation I had before, 6RL over 8LW squared for our maximum flexural stress. Now we can move on to ACI 530 to ensure that the brick formwork has the capacity to resist this loading. This should be pretty familiar now from our component analysis section on the ramp walls. We'll start by turning to section 8.2.4.2 regarding flexural tension. Because the tension from flexure is parallel to bed joints in the running bond, and is parallel to the bed joints, and we have our brick formwork in running bond, as well as hollow units that are fully grouted with Portland cement, we can take an M allowable of 736 kilopascals and compare this to our maximum moment. M allowable, or our allowable flexural stress, in this case I've kind of mislabeled it, of 736 kilopascals. You'll see the units work out, and we'll compare that to our maximum flexural stress. And regarding shear, we do a similar calculation from the component analysis section, where we check conditions A, B, and E. C, D, and F are not applicable in our case. Section 8.2.6.2 also says that we can be using these equations for both in-plane and out-of-plane shear stresses. And we get a governing value of this point A of 58.1 psi, and we want to check that to be less than our shear stress, FV. And this is how we check that the formwork is adequate in adequate strength to resist the hydrostatic pressure from the concrete.